Good morning. My name is Palmeira. I'm a PhD from University of Tours in France. I work with professors Nisa Messi, Yassine San, and Thomas Devogel. First of all, I'd like to thank the members of this prestigious conference for this opportunity, and especially to Professor Kari. Please allow me to present my paper entitled User-Side Service Synchronization in Multiple Devices Environment. Our outline is proposed like this: an introduction, a motivate scenario, cube model formal description, implementation insights, feasibility test, results and evaluation, and we finish with conclusion and future works. Today you have a such scenario: a user that owns more than one connected device and we use these devices to explore web service daily. However, these devices don't communicate with each other directly, and then we must pass by a third part, such as server or a cloud-based system, to synchronize the web services deployed on these devices. I can summarize our scenario in the following topics: everything as a service, cloud-based system behavior to user and the solutions, interoperability problems regarding operating systems and services, multiple devices environment owned by a single user, and we have liquid software as an alternative for server cloud-based system for client-side approaches. So today we have this scenario with the synchronization of data session state made by the third-party provider. We are able to move with our mobiles and make use of web services at the same time. However, we can make a question. It is possible to use web services without continuously depending on a servers. So this motivating scenario, we have a resource limitation for a given device. For example, the keyboard is too small, or screen that perhaps is too big, etc. We have high internet dependency for all web services tasks, high traceability of devices towards the internet, that means low privacy. Available technologies apply for more recent devices, and mobile resource not explored for web service locally. Our purpose in this paper is to reproduce such a scenario where multiple devices can send and receive web services continuously. More technically, using liquid software principles as an alternative to server cloud-based system solutions to use web services in a multiple devices environment, regardless of the operating system, in a synchronized way and without entirely depending on the third part. Continuing on our outline, we have the cube model formal description. With REST and RESTful presents a lot of constraints, specifically how we can provide automatically scale out of a service in a multiple devices environment, how to understand the traceability of devices and services with a single user, and we'll try to graphically represent the cube elements. That is why we decided to present in this paper the cube formal description. We have six basic elements that we understand necessary to explain how the cube works. These elements are the adaptation of the user-centered network for a single user, an individual user, a single device, multiple devices, one service, and multiple services. So in the following slides we have the description of each of these elements and the set of devices, the set of services as well. So when you have introduced these elements, we can finally build the elements that compose the cube. Then in definition 2 we have the inner cube. The inner cube is the combination of the set of devices with the search engine. Then definition 3 deals with the outer cube. The outer cube is a representation of a set of services plus the search engine. Then definition 4 brings the pool area. The pool area is the space between the inner cube and the outer cube. That space is the responsible to allow the communication between device and services and change the state in the hypermedia in this space. So it's in the pool area that conversation happens between devices and services. Finally, definition 5, we present the cube. The cube defined as a platform formed by user, surrounded by a set of communicating devices, the inner cube, a set of services, the outer cube, and the established connection between them, the pool area. Continuing, we have our implementation insights. We have challenges regarding loose and tight coupling web services. Work toward native apps was a really challenging trick because each operating system has a different way to treat native apps. HTML5 is limited regarding some plugin devices, and we think in a token to protect and encrypt all incoming communication. To then, we propose to enhance our logical dock to deploy web services and add devices. So the screen on the left, we have the basic logical dock representation, and you can note the unnamed device like this. Then on the right, we can able to grant an ID to a device. So with this, we can provide a token for communication and data encryption. As we deal with web services to a streaming, such as YouTube, user experience analysis indicates the best way to put the cube as a browser extension. So you decide to put the cube on the right corner as a small button. So if the user decided to liquid this page, it's necessary on to click. So this is another perspective. And when the user decides to click on this button to liquid this page, he has the available devices. So all the devices he can switch the content what he saw. So continuously we have the test. So the test consists with 10 persons, and this person should migrate a video towards 5 devices with and without the cube. So no previous training was required. The purpose of this test is to evaluate the wasted time to play the video. So the set of our devices it's composed by 3 desktop units, 2 tablets, and 1 mobile device. What we achieve as results, RESTful principles achieved, such as high interoperability, security in all devices, and system performance. Also, we respect RESTful constraints, such as stateless interaction, resource linking, uniform interface, and hypermedia for decentralized resources. We achieve traceability of devices without compromise the presence of all involved devices. So we have high privacy in these results. That means when the server side look for the specific device that play a given video in a given moment, the only information the server side holds is regarding the first device, even if the reproduction is already in the second, the third, and the fifth device. So the server side is not aware about the migration between devices. Using the cube, the server side was not aware of the service migration, so for the user side, only resume task. The cube work is responsible for maintain the state of the services, even if the server cloud was present. So we have the evaluation. With the cube, user spent 5.8 seconds to migrate all the video across the devices, as you can see on the left graph. And with this, user up to 12 times faster when you use the cube. Without the cube, users spent 68 seconds to migrate the same video across devices. So you have the set of the 10 scenarios. On the left graph, we have individual analysis for the video, and the right graph is the total for migrate each video with and without the cube. So I finally conclude this presentation saying the cube using Liquid software as an alternative for cloud server-based solutions, available for loose and tight coupling services. We mentioned the tight coupling service as a YouTube stream and focus of this paper. Faster than traditional server-side synchronization for streaming services. As future work, we think to deploy other metrics based on the system usability scale formats to measure another parameters from the cube. And also we are modeling the cube as a cluster model system for locally enhancing processing and storage capacities for given services for IoT devices and large scale scenarios. Thank you very much for your time and your attention. I'm able to answer your questions now.